5 seconds.
We are Stoke Space. From seed money to engine testing, we've moved faster than any rocket company in history. We are building the holy grail of rocketry, a fully and rapidly reusable rocket. Our singular focus on 100% reusability and ultra-high launch cadence drives every architectural decision we make. So, we started with the second stage, the stage everyone else throws away. Our unique innovation is a combined system of 30 smaller, independently controlled thrusters embedded into our dynamically cooled heat shield. In the vacuum of space, our second stage separates. The plumes from 30 thrusters merge as one to provide ultra-high in-space performance. We can precisely deploy our payloads when and where they are needed. Once deployed, our second stage deorbits and begins atmospheric re-entry. Our durable metallic heat shield protects both the vehicle and return payloads, abandoning the industry standard of fragile ceramic tiles. Once safely through the atmosphere, our engine fires up, providing low throttle thrust to enable precision landing. The active cooling of our heat shield leaves the vehicle at a low, approachable temperature in preparation for rapid reuse. We are Stoke Space, and we are building the world's most efficient, fully reusable rocket. One mission-affirming piece of hardware at a time.
Stand by.
Real hardware, real results.
I would say first, it was an evolution. It wasn't one morning I wake up and decide to start the company. But look, I think when you look at the economics of launch, the economics of full rapid reusability are so powerful that there's really no other future end state, right? So to me, that is inevitable. That will happen, full and rapid reusable rockets. And if you look out on the landscape, number one, there's only one other company pursuing that. It's called SpaceX. And when you look at it from a technical perspective, it's my belief that you really have to design that from day one into the vehicle. You can't kind of back your way into it later. And so, when I was kind of thinking about what I wanted to do next, I looked out on the landscape, and it was, honestly really surprising to me that nobody else was pursuing it. And I think that there absolutely need to be more than one player to have a healthy economy for space mobility. And so there's got to be somebody else other than SpaceX doing this, and it wasn't out there yet. So here we are.
So here we are. Excellent. So that's what you did. I mean, you didn't come straight out of getting a doctorate in aerospace technology into creating a company. You did a couple other things first, but you sort of got to the point where you said, something, nobody's doing the exact stuff that I think should be done, right? And so you went off to found Stoke Space. Is that sort of how it went? Instead of taking these ideas somewhere else, like what you're doing so radically different, you decided to do it right. We need to be in control of how it's working.
Yeah, I suppose. I spent about 10 years at Blue Origin first doing engine development, and really cut my teeth on that. In fact, worked BE4 for a long time, and so I'm super excited for today to see them fly finally.
Excellent.
And I think I learned a lot. I think the market has changed a lot in those 10 years. So this is, call it 2009 to the next 10 years or so. And what you saw happen was, first of all, commercially viable business cases actually started to emerge, especially as SpaceX started to improve the cost economics and availability of launch. So you finally had, viable business cases happening. You've got this really exciting new, talent pool within our industry that really hasn't existed before, where you have people, something like me, who have kind of gone through this process of blank page all the way through flight, maybe multiple times by now, and really done so with pretty small teams. That talent pool didn't exist in 2010, right? But it exists now. And then the third kind of ingredient that really, gave me conviction that now is the time for commercial space to really take off was the technical tool sets that we have. We can do so many powerful things with modern computing and analysis tools, and so that you can pull this stuff off with a very small team on a relative basis. So you have those three kind of ingredients coming together for the first time ever. It makes it really, really exciting in our industry. I think that's why you're seeing so much activity. And I think now is the time to knock that last domino over for the industry and get after vehicles that come and go to space, every day.
I like it. And what you said is something that we don't think about very often. Like, you used to be these big monolithic organizations that needed to develop these things, right? And with the tool set, sort of the way that technology has increased, and we don't have to go out, we can simulate so much stuff. We can test things before we really dig into it. And the ability to dig into it, like after we've made technology, we've made the hardware, we go out there and we do the engine tests. You're right that we used to not really have that ability to work on this sort of scale, and now smaller organizations, I guess, can be so empowered to go out there and test things. So you've got so many things like this, right? You didn't just say, okay, here's what a rocket should look like, and now I'm going to make another rocket that looks like a rocket should look like, and it's going to have a little pointy end up here, and it's going to have a little nozzle that fire comes out of. Like, your rocket is similar because rockets like rocket shapes, but it's got some different pieces. Let's start talking through some of the technical differences about what Stoke is working on and how it's different than what anybody else is doing right now. Where do you want to start with that? I mean,
yeah, that's a big question. I think maybe start at the very beginning, right? 100% reusable rockets. That's the inevitable end state. So that's my conclusion number one. Conclusion number two is you can't back your way into it and figure it out later. It has to be designed in from day one. And
right.
so once you have those two pieces, the third piece is, okay, what's the part that the industry doesn't have a playbook for yet? And that part is the reusable second stage, upper stage. And so that's where we started to think is, and it was important for us. First of all, my co-founder, Tom, and I basically left our last job with that much in hand, right?
Right.
We didn't really have any solutions. So the first piece of this was, can we take that question and turn it into an engineering problem and not a science problem? It was really, really important for me to have my own conviction that this is something that is, I guess, responsible to take somebody else's money, namely, venture capital or whatever, and go and put something together that was executable. Okay, so we're trying to solve this reusable upper stage problem. Obviously, the thing has to go and deliver things to orbit. That takes some amount of high performance in order to be able to go and perform that function. But then to get it back, it's not enough to just bring it back. It has to, if it's going to be rapidly reusable, it's got to land and fly as fast as possible. Our mental model is we want to turn this thing around in a day. So if you do that, you have to think about at least as hard about what you cannot do as you think about what you can do in those 24 hours. And I guarantee you, if it's gonna turn around in 24 hours, you're gonna be pretty damn busy restacking the vehicle, reintegrating payload, getting it back on the pad, refueling, and flying, right? So there's absolutely no time for inspections between flights. There's no time for refurbishment for sure. So this thing has to be bulletproof, right? And this is the way we operate. I mean, it sounds kind of radical maybe, but this is how we operate aircraft every day. They're not inspecting the damn thing between flights.
More of a walk around, right? They're not going and opening every hatch and stuff like that.
Pre-flight check. Yep. And so, so we do that. We do that a lot with, built-in bit checks and software and obviously visuals. And you see that happening on other vehicles that fly as well. But anyway, so that's what you have to spend your time on. That's it. Right. And so there's no inspections, there's no refurbishment. And because of that, you need some re-entry method that's just bulletproof. And when we think about the traditional ways to bring something back from orbit, there's really two. One of them is the ablative heat shields that burn away between, on the way in. And that's a perfectly robust system, but it's just not reusable. So that's out. And then the second thing is, kind of the ceramic tile solution that shuttle used, X-37 uses, Starship is using, and man, that's a technical challenge right there, in my opinion,
Right.
on this rapid reuse problem. There's two challenges. One is, first of all, there's thousands and thousands of tiles on Starship and shuttle and whatnot, and every one of them has to stay bonded. So that's challenge number one. And challenge number two is, please don't crack them, right? Don't crack them from things like micrometeorites, bird strikes on reentry, even mundane things. If you think about long service life, you're going to have, technicians bumping them, dropping wrenches, whatever, right? And what do you do then?
The engines are going to ignite of some sort, like.
Yeah, right, exactly. You're gonna have debris. So what do you do then? I don't know. Are you happy going without inspecting? And my position is, you have to be happy to go without inspecting, right? You have to, because these things will happen. It's inevitable. So that's the question. And us being engines people, we cool the inside of rocket engines with this really very powerful cooling strategy called regenerative cooling, right? Where you're pumping propellant through coolant channels in the skin of the engine. And we cool engines regularly at, the heat, the thermal environment in there is about 10 times higher than the thermal environment from reentry. And so, when you come from that world, the thermal challenge is not actually that hard. And so we thought, wow, this is a very powerful mechanism. Can we use that and extend it to the entire vehicle, and do so in a way that's mass efficient enough, and I guess performant enough from an ISP perspective? And so, so that's the evolution in the thought process. Now the question is, all right, how do you do that? Do you cool, bring it back capsule style and cool the base of the vehicle? Do you bring it back in the belly flop strategy, Starship and shuttle style? And for a number of reasons, we settled on the capsule base first reentry strategy. One of those reasons is cryofluid management coming back in. The belly flop has a cryofluid management challenge that, Starship, we saw them work through that. It was very impressive. But still they had to do that. But there's all the slosh that gets introduced from that maneuver. Yeah. From a payload perspective, we're able to design a thing where all of the loads are in the axial direction, whether it's on launch or reentry. And so from the payloads, you can design your payloads to take the loads in that direction. You can also design the vehicle to take the loads in that direction. So you get some efficiency there. And so we liked that. And then from a surface area perspective, you have to cool maybe a smaller surface area than you do if you bring it back belly flop first. Okay, so now we're there,
right?
Yeah.
Like real quick, there's a trade-off, because if you use the broad side of the barn, right, you can get more drag to help slow you down more quickly, but you have a much larger surface that you both have to deal with cooling, and you also have to deal with inspecting or making sure it's good to go for the next flight. So if you're just protecting the bottom of the vehicle instead of the entire side of the vehicle, not only have you diminished this, or I guess optimized the surface area you have to protect, you've also got a smaller surface area that you need to make sure is good to go for the next flight, right?
That's right. Yeah. Yeah, 100%.
Cool. All right, folks, real quick, there's so many questions that are coming in as well, and I will try to get to some of the questions, but Andy is mentioning so many different things here, like when he just talked about the structure, and then you have the vertical integrations versus the horizontal, and the loads are going this way so you can be more efficient because you don't need to deal with it. Like, there's so many things, and he says it once in a sentence, and then 15 questions come up like this. We will try to dive into some of these things, but right now we're talking a little bit high level about why, like, how did you get here? How did you think, let's design this vehicle? Not trying to shoehorn in like, well, we have a second stage, what if we put a heat shield on it, right? It's we want something that comes back from space. We can't do it traditional rocket style, which is throw pieces off as you go to become more efficient, right? You need to bring most of your pieces back, except for the fuel you throw out the back, right? But we're sort of talking through this right now. And Andy, you say so many things, and I'm like, that could be a 30-minute discussion, and that could be a 30-minute discussion.
Well, I would say a lot of thought did go into it. There's one more step, and that is, okay, now we've got a capsule coming in base first. It's regeneratively cooled to cool it. The last question is, how in the world do you bury a high-performance upper stage engine into a heat shield?
I had that cuddling Kerbal.
Yeah, exactly. And so that's kind of the last question that we had to ask for ourselves. Went through many different interesting designs to get to where we are. And I think most of the audience probably knows it's a set of discretized thrusters fed by a single set of turbo machinery arranged outside the perimeter of the vehicle, and makes use to some extent of the Aerospike effect. But certainly it's not like we set out and said we're going to design an Aerospike. It's very different for various reasons. It's very different from a traditional Aerospike.
Yeah. Can we get a photo? There we go. There's a photo of the bottom. So is this one engine or is this multiple engines? Does it really, like, what is the differential between how you define how many engines this is?
I don't know the answer to that question, actually. But I do know, I consider it one engine. It's certainly one engine program. It's a single set of turbo machinery. So there's one turbo pump for the fuel. There's one turbo pump for the oxygen. And it feeds a common distribution circuit, which is actually the heat shield. And from there, it feeds all of the discretized thrusters around the perimeter. In this picture, we have 15 of them installed instead of the full set of 30.
There's just like blinds in between each one, and there should be double that many in a normal loadout, I guess.
Right.
All right.
That's right.
So does everybody understand sort of what we're talking about here, right? Those rocket engines look funny because it's not one bell on the bottom of the rocket, or 5 bells, 7 bells, 9 bells, right, that are down at the very bottom. You can see the curve. I guess that's the tank there, right? Did this one have the heat shield on it?
The curve on the bottom is that what you're referring to? It was taking all
of this image
fire
here.
Yeah, that is the heat shield. Yep.
That is the heat shield.
That's the heat shield.
So you don't have the engine in the middle, and then you have to deal with the fact that all your engine hardware or the nozzle or the thrust has to get through the heat shield somehow. What Stoke has done is they put the engines around the outside. In the center is just the heat shield. But what Andy just said, there's one set of turbo machineries and one sort of distribution. That means every little flame you have there doesn't have its own discrete turbo pump to pull the fuel out of the tanks and stuff it into the engine, or I guess here through the heat shield and then into the engine, right? It in one distribution channel, like it's all going through one system. So that's sort of where you get into how many engines is this. You couldn't take one of these nozzles off the side and be like, here is an engine, it works on its own. Like they need that single turbo machinery and distribution system to feed the combustion chamber. So one set of fuel and distribution, multiple combustion chambers, you're gonna have 30 around the base of it. Look at that. Andy, when I saw that at first, I was like, what is this company doing? Like, that's not what a rocket engine is supposed to look like.
Yeah, it's
you
weird.
Get that. You don't have to penetrate the heat shield. You have it around the outside, so you can have that single, I guess the single piece heat shield, I guess not technically a single piece, but you know what I mean. The engines aren't poking through it. They're around the outside. How do you steer, though? Like a normal rocket engine, it needs to waggle. TVC checks. Those are super important.
Yeah, this is great. That was one of the next questions, right? Not only do you have to bury the engine into the heat shield somehow, but you also have to steer the rocket. Yep. And similar to ceramic tiles, if you have a gimbaled solution where you're swinging the engine around in order to steer the rocket, somewhere in there by necessity will be a hot gas dynamic seal. It has to be, right? And similar to the ceramic tiles, Tom and I kind of looked at each other. We were working through all kinds of different ways we could package such a seal. And we're just like, dude, we will never trust that thing. No way.
Right.
Maybe it'll work the first time, but not on flight 50 or 100 or whatever. And so that also contributed to the final layout here where the thrusters are on the outboard side. They don't swing, they don't move. And the way we control the vehicle is through what's called differential throttle, where we'll throttle up one side of the vehicle or the engine and throttle down the other side in order to give a pitching moment on the vehicle.
Gotcha.
Yep. And so all of those thrusters are all they have individual throttle control ability. We actually have throttle control in 2 different places. One's with the pumps. So the bulk engine thrust can be throttled, and then the relative thrust from one side to the other can be managed by the individual thrusters.
So let me unpack what Andy just said here, right? You have the engine, and if the engine needs to drive the rocket by vectoring, right, by waggling back and forth using like a thrust vector control, you have moving parts. And so that's all good and well when the rocket's going up and all the force, the aerodynamic forces are on the front of the rocket. That's why you have the pointy end at the top of the rocket, right? Behind it, where you have the engine and the boat tail, you really don't have to worry about air trying to, you should probably have to worry about it a little bit, but force its way in between the engine bell and the rest of the boat tail and the machinery and getting into your cavities where all this stuff is protected, right? But then turn the rocket around and have it come flying tail first. Now, when it's re-entering, all of a sudden the forces are reversed. I guess maybe not technically reversed. The rocket direction is reversed. And so the forces are hitting the bottom of the rocket and not the pointy end of the rocket. And so how do you keep, with these little waggly machineries that have to have seals around them, how do you keep that from impinging up past the seal and getting into your machinery? Right? That's what Andy was sort of saying there about the seals, and you've solved that by removing the need for the engines to. I like this waggling motion, by the way. Like, everybody knows what I mean. The engines.
Yeah, the best part is no part.
Yeah,
the best part is no part. So design it out. That was the answer.
So how do you steer the rocket then, right? So your engine nozzles are fixed, and you can't just waggle it in one direction. So you get a little bit of a lever arm, so you get some torque, so you can turn the rocket one way or the other, right? Pitch and yaw the rocket.
Yep.
So how do you steer the rocket? That's where the differential thrust comes in. And so Andy just said two things. The turbo machinery, remember we said the turbo machinery is all one set and it feeds all the engines. So your gross throttle, like for all of the engines, you can change the flow through that turbo machinery that's feeding the engines, and that'll change all of the engines up and down. And then if you want the rocket to lean one way, well, your engine can't waggle. So what do? You put less thrust on one side. Well, I'm going to say more thrust on the other side, but maybe it's just less thrust on one side and then it leans in that direction, right? And so there you can control the thrust of every one of the independent engines. Is that with there's like a valve or a pintle or something like that? How do y'all lessen the output on one nozzle, one combustion chamber?
Yeah, they each have their own throttle system, which is, let's call it a valve. Yeah.
Gotcha. A valve.
Yeah,
all right.
It's kind of integrated into the head end of the chamber there.
Gotcha. So you have your entire thrust with the machinery as a whole that feeds all the engine, which is, you're coming in for a landing and you need to throttle down so you land and you don't take back off again. And if anybody's ever done that on the moon in Kerbal. And if you need to steer the rocket, you turn down the engines on one side by sort of limiting the flow through them. That gives you less force on one side, the same force on the other side. So you have a torque, you have a differential there, and the rocket starts to turn. Is that what it works? Like, is it stays constant on one side and lessens on the other side?
There's different strategies you can use, but and typically it depends where we are in the mission also. If you're operating the engine 100%, then yes, and you typically don't need as much control authority at that point. If you're operating the engine at 50%, 40% power or whatever, you do have the freedom to go up or down, so we use a combined strategy, let's say that.
Gotcha. A combined strategy. And Andy, if I start to get too much into the weeds, just be like, dude, seriously? I'm super interested in how this works because you say, oh, there's two strategies. Well, there's two theoretical strategies, but you're the company that's sort of making this rocket science into rocket engineering, right? You're making hardware that does this stuff.
So you can see it happen. If we have the, I don't know if there's Hopper video on here, but you can kind of watch the strategy go up. We took off from the ground pad or whatever you want to call it, concrete slab.
Yeah.
And then you'll watch the vehicle kick over, at a very prescribed point in flight, and then come back down. But that's it, right?
First,
you described it better than I can.
Test. I say simple test, right? But there it goes. By the way, that's not tethered, is it?
It kicks. No, it's not tethered. That was a exciting point of discussion for us internally. Do we tether or do we not tether? And ultimately decided, well, we can talk a whole lot more. There's a lot that went into this test, and there's a lot that I guess went into determining the flight profile there too. But you can see the differential throttle kick in as the vehicle goes up. I don't know how high, 10, 15 feet it was before it kicks over there.
And it does kick over. Like when it kicked over, you saw it move.
Yeah, the idea was go up. We didn't want to land exactly on the spot where we took off. So kick over and see if we can land it a little bit further away.
Just to demonstrate some translational control authority, because it's all good if you can go up and down. But the important thing is, do we have the authority to start a move, and then recover control, like stabilize while moving, and then stop a move, and then come back down again. You think, oh, it's super simple. It just took off and it landed again. It went over a couple feet. Think about the discrete steps that have to happen in order for that to land on the ground in one piece. I'm going to come out there and do a FOD walk for y'all, by the way. If that's
well, I will say for things like this, you'll think you get everything, and then even through the course of the day, if stuff's blowing, it's just coming off of a concrete slab like that, right? So all kinds of stuff.
So no kidding. You solved a couple of the different problems there. You want this thing to come all the way back from space. It's not something that's been designed or in wide use or something. You have a capsule, and if a capsule comes back, it has a heat shield on the bottom of it, and the capsule slows down by the aerodynamic forces on the heat shield, and then parachutes, right? But you want to land with engines. You have to have those engines pointing down. So all of the things we've just talked about are probably like a very small 25-minute slice of the things that you had to think about in order to get this far. And we haven't talked about 1/10 of the things you had to think about for this vehicle. So let's move on to other things. We didn't unpack the regenerative cooling that much. You talked a little bit about you have tiles or you have this regenerative cooling. There's a different way there's multiple different ways you could do that. You could have a coolant, you could have water, it could come out and be thrown overboard. And what did y'all decide to do with the regenerative cooling to support your idea that you wanted this thing to be rapidly reusable all the way to space, all the way back down again?
Well, I think the first thing is you got to do all those things we just said, but it still has to perform its function, which is to deliver payload to orbit. And and because of that, it has to be very mass efficient. Now we could talk about sizing the vehicle and all of those things, but the bottom line is we wanted to build something that's complementary to Starship, right? The way I think is you have to hope and expect that Starship will be successful, and when it is,
right.
That's a very exciting day for all of us, and we want that to be good for us, and I think it will be good for us. But that means we also have to be competitive with the Starship world and be also different, right? We have to offer something unique. And I think the medium class rocket does that, provided that we can match them on price and cost, also kind of provide something unique in terms of availability or accessibility or size, direct to final orbit, et cetera, et cetera.
Gotcha.
Okay, so the point of that is, go ahead.
Just real quick, the analogy on that, because I hear this all the time, and we try to help educate people. Oh, once Starship is flying, we won't need any other rockets, right? Well, I don't want a cargo ship delivering my Amazon packages to my front door. I don't want an 18-wheeler trying to go through the turning circle, right? I don't need these huge monolithic things that are taking huge amounts this distance. We need sort of, I don't know if last mile is really the right way to say it, but that's what you're talking about here. It's not that Starship's going to do every single thing and we don't need any other rockets. We may still need final mile, for the lack of a better analogy, right?
Yeah.
I guess it's not really even final mile because it's not.
You can think about it final mile. You can think about it as express shipping. You can think about it any way you want. I think, very fundamentally, economically, you don't want a monopoly either, right? You don't, right? In order to have a healthy economy, I don't. Yeah, you don't. And so, it's especially true as companies start to go into other, verticals. You want healthy competition in each of the verticals. And so if you have one company controlling access to space and you have one company controlling telecom, it's going to be very hard for any other company to enter that space because they're at a fundamental disadvantage without owning mobility, right? And so, I think even SpaceX wants, they may not admit it, but I think anybody who wants a healthy economy in space in the long term, there needs to be some level of competition, right? Yeah. So that's part of it. And what I was going to say earlier is, if you're building a medium class rocket, you don't have the economies of scale at your advantage that something like Starship does for the actual mission, delivering the thing to space, right? So you're working on a smaller scale, and the whole thing has to be mass efficient enough to do it. And so that feeds into our technical design as well.
Right. And we were getting into the regenerative heat shield being mass efficient. You don't want to carry things that you don't have to, right? That's the huge thing about the rocket equation, rocket science, like figuring out exactly how this math works. If you carry things on your rocket that aren't fuel, aren't payload, that means that you have less ability to carry fuel and payload. So you get into the materials your rocket's made out of. You get into things like, well, yeah, we could cool that heat shield with water or something, right? Well, what else is the water going to be used for? Is it going to be dead weight until we use it for the heat shield? And that's where you got
Yes.
into this idea of using your propellant to cool the heat shield, right?
Yeah. Yeah, water is an extremely efficient coolant, but you're right. If you use water as a coolant circuit, you need an entirely separate system. You need water tanks. You need the water itself. You need water pumps. You need all of those things, and they are exactly what you said. They are dead weight. They're pound for pound. They are dead weight for the entire rest of the mission. Hydrogen is part of what led us to use hydrogen in the upper stage. Hydrogen is extremely efficient coolant. Also, it's about, depends on where you are in the temperature range, but between 5 and 7 times better coolant than really any other propellant that we use in rocketry for cooling. And so it's extremely efficient there. It also gives you very high specific impulse. And so anytime you're bringing back the second stage, you need to build that elbow room into your design somehow in order to pay the reuse penalty, basically, right? So you can't pay the reuse penalty if you have no margin to begin with. So where do you get that margin from? Hydrogen gives it to us. And then it also creates a very efficient means for cooling on reentry. And we're able to basically use all of the systems that we already have on board to do the ascent part. We just use them again for the reentry part.
Right. And so, like, to explain what this means, like, the hydrogen is actually not only used as the rocket fuel, right? But you're also flowing that hydrogen. I mean, sometimes you use the propellant itself to cool the engine. You're flowing the hydrogen through the engine bell, through the heat shield. Of course, you're flowing
through the heat shield. Yeah. If you find that picture, if you find the picture of Hopper where you're looking up at the heat shield, it's gonna see if you can find that. Pull that up. But
we get there.
Yeah, there you go. So you see, there's like white stuff on the bottom of the heat shield. That's frost. All right, so we are flowing liquid hydrogen through that heat shield. It comes in the center of the circle, basically, and flows radially outward. And it's cold, right? So that is frost on the heat shield. The whole thing operates at a very low temperature, and then comes down and lands, obviously. What was I going to say? Oh, and so this is operating in the day. And one of the things, if you're familiar with hydrogen fires, you really can't see them in daylight. Clear. Beautiful at nighttime, but you can't see them in daylight. But there is a raging fire happening right under that heat shield, including where the ice is, and that's kind of cool. You saw the picture earlier of the engine on the test stand where you could see, it was a night picture, you could see all the fire underneath. You're basically looking at the same thing here, you just can't see it. So even though there's fire right there, yep, there you go. Even though there's fire right there, it's it's frost. Yep.
So you take the hydrogen, you flow it through the heat shield. That helps keep the heat shield cool. You flow it through the engine. That helps keep the engine cool. It flows through pumps. That helps the pumps, right? Like all the different things that it does. But one of the critical things here is you're not carrying something else. It's not heat tiles you're going to have to inspect and replace, right? It's not a different coolant where then your plumbing becomes more complicated and you have to stuff more tubes, and maybe you have a couple more tubes in there for these little crossovers and stuff, right? But it's not a completely different system with completely different pumps and tanks, like you said. So that's what probably one of the, I guess you could say, genius of using this single thing. You're carrying it anyways. You're going to use it to get into space, deliver the payload. You're going to use it to cool the heat shield when you're coming back in. You're going to use it to land too. And that one propellant, that hydrogen, does all of those things for you. That's cool.
That's right. Yeah, and I guess you hit on another thing that we didn't talk about yet, but it's a high-performing upper stage engine, and so in vacuum, you want a very high expansion ratio in order to get the performance right. But it also has to operate at sea level on the ground at very low throttle. And so that factors into the equation also. How do you achieve that with a high performing upper stage engine? You can't do it with RL10, Right. And so this set of discretized thrusters, with making some use of the Aerospike effect, it kind of does that function for us. By the way, that's also why there's only 15 thrusters installed on Hopper instead of all 30, basically running this thing with empty tanks and no payload. So we are mimicking the landing phase of flight when the whole thing's empty. There's not much mass in there. And so it's operating at very, very low throttle for this entire mission, the quote unquote mission, the Hopper mission. And we don't, part of the way we get the deep throttle is by turning off half the thrusters. And in Hopper's case, we just don't install them because why put them at risk?
Why put them there? Yeah.
Yep.
Keep them in the barn, keep them in the parts inventory, right?
That's right.
Let's talk about that just a little bit, because these concepts are so cool. I want to make sure people understand. Andy mentioned expansion ratio, right? And so, or if you've watched our channel enough, you know that there's probably different types of engines, and some engines are great for operating at sea level where there's air, there's atmospheric density around you, because that atmosphere sort of helps keep your exhaust. I talk about it, I've drawn it before, in a little pencil flame, right? And then every launch, I'm like, oh, you can see the expansion. As it gets into the thinner atmosphere, the plume expands out. It gets bigger, right? And there's less atmospheric density to sort of push that plume together, and it's not a pencil anymore. It's a big plume, right? But when you get into space where there's no more atmosphere, you have to provide your own flow control, I guess. It's the engine bell. You see the engine bells on the engines that are optimized for space, and they're really huge engine bells, because when there's no atmosphere to help you out, you have to build a physical structure that keeps the exhaust going in a direction so you can get more energy out of it, right? Well, these are tiny.
Yeah, you get more
bells.
efficiency, you get more expansion, you get more thrust out of it, so it's a higher thrust, higher efficiency.
Yep.
So you want you want that to be as big as possible in space.
And then here on this design, these are all like small engine bells. We don't see, like, look at the CSM that went to the moon and that massive engine bell on the back of it, right? These are all tiny engine bells, but then how do you get to use this engine in both of these multiple regimes? That's the Aerospike effect you were talking about, right?
That's right. Yep. Yeah. So, in the pictures that you saw, it's obviously operating in sea level. So the engine plumes, like you're saying, come together pretty quick. They're like very linear plumes.
Yep.
Excuse me, by design.
Plumes.
And then when, little pencils. And then when they go up into I guess the vacuum of space, those plumes expand and they actually merge together. And then they kind of create this continuous annulus around the heat shield. And then they trap some gas in the center core, right? So underneath the heat shield, they trap some gas, which is kind of the same thing as trapping some pressure. And so you get some pressure on the base heat shield there, and it's multiplied by an enormous area, huge area. Yeah, there you go. That's the picture.
Yep, that's it.
And so you get some bonus thrust just by the gas and the pressure that gets trapped in the center there. That is the Aerospike effect, right? And we make some amount of use from it. Yep.
Yeah, like you said at the beginning, you didn't set out to design an Aerospike engine, but because of the way you're doing things, you get like a little bonus from the fact that this is probably too much of a stretch. I don't have a doctorate in rocket science, but the engine exhaust is almost acting as the engine bell to help you constrain that and get a little bit more bounce for your ounce, or whatever you want to call it, right?
Yeah, no, exactly. That's right.
All right, good. So it's amazing that you did that, and you've got that sort of design. So many different things going into the fact that this needs to go all the way into space and do its thing, and then come all the way back down again to get turned. Walk around it, kick the tires. I guess it doesn't have tires, but put a payload in it and send it again. Let's talk about materials. So we talked to different rocket companies, and there's different camps of the materials that you actually build the main structure out of. Y'all have gone with I say more traditional. It's probably the wrong way to say it. Stainless steel, right?
Mm-hmm. Yeah, I think one of the things that the industry is learning as a whole is that there's a huge amount of value in being able to manufacture at high speed, especially during R&D. And so you want to be able to build fast. You want to be able to iterate fast. You want each increment to cost as little as possible. And so I think manufacturing kind of dictated this trade as much as anything. In this case, we chose stainless steel, as you said. This allows us to, first of all, there's it's a commoditized alloy that we buy off the shelf from any number of suppliers in just like raw sheet metal form. So that's number one. Number two, it's pretty easy to work with. So that's good. We've come up with methods to build these structures that you're showing with really no fixed tooling and do so at a very high clip. there's talent base that's worked with it quite a bit. You know, it's not super esoteric where you can only pick from 3 people in the world to be able to work with this stuff.
Right.
And so a lot of things, you know, you have to think about all of those things. Now, when you look at it from a technical trade perspective, yeah, you might be able to use, you know, high strength aluminum alloy to, on paper, get yourself a little bit more performance. But how are you going to get from nothing to market as fast as possible? It's a close enough trade where, to us, the manufacturing wins out every time. The other thing for the reusable second stage is that this thing is going to come back, and it's going to come back in a very hot environment. We have the heat shield on the forward side that's taking the brunt of the heat load, but the sides are also going to get hot. And so stainless has a much higher, I guess, heat tolerance or strength at temperature than aluminum would. So it helps us from that perspective as all. There's an anecdote that not many people know about, but shuttle came back, and here's another element of regenerative cooling over tiles. So shuttle came back, and you're coming back, the tiles are glowing white hot or red hot or whatever, and they're amazing insulators, which means the heat flux through them is very low. It takes time for heat to get from the hot side over into the structure. But at the end of the day, they are absorbing heat through that whole phase, right? So then it landed, and the heat is continuing to soak in the tiles. Tiles are still very, very hot. And so they actually had to plug in a separate water coolant circuit to shuttle when it landed in order to cool the structure so that the aluminum didn't overheat and lose its strength properties, right? No time for that. For us, we want to land. We want to land and get moving. Right. So I guess there's twofold. One, stainless steel is not susceptible to that as much. And two, it's the regenerative part. It comes back and it lands cold, right? It lands cold because it just had liquid hydrogen flowing through the whole thing in order to perform that landing phase, right? And so the whole thing is cold and approachable right from the second it touches down.
Yeah. It's the different schools of thoughts there, right? Because we've heard of other rocket companies that are using carbon composites, right? And this very complicated thing, we're going to wind this up, we're going to build it, but that sort of makes a little bit more, I guess, slows you down in the manufacturing part a little bit. And with
I would say that the manufacturing is slow and expensive. They are right? There's 2 ways you can hack the rocket equation, which is, by the way, very, they talk about the tyranny of the rocket equation for a reason. We're in a planet where we can just barely get out of the gravity well with chemical propulsion. And so there's 2 ways to hack the rocket equation. One is with efficiency, specific impulse of your engines, performance of your engines. The number 2 part is with a mass fraction. So you make the whole thing really light. And that's what the composites do. But it makes manufacturing very expensive and pretty slow. And then, there's some amount of question about how that survives reentry heat as well.
Gotcha. You said a fixed tooling. So the structures that we were looking at were made mostly with no fixed tooling. Tell me if I'm wrong when I translate that a little bit. We've seen rocket factories and it's like, here's this massive press that does this one thing. It's going to make this grid structure out of aluminum and make this tank. And it's this huge, massive thing. Is that what you're talking about when you mean no fixed tooling?
You just described fixed tooling. Typically millions of dollars in fixed tooling goes into this type of thing. And yeah, it was important for us to not do that because first of all, we're a startup, we can't afford it. And second of all, we do want to maintain flexibility, right? Once you have all that fixed infrastructure, let's say you want to change the diameter of your tank by a little bit while you're hosed, right? So then you start getting things locked in and you really lose the flexibility to evolve, with yourself and with the market.
Gotcha. So you did not, you're still developing things, you're still testing hardware. You're not to the point where it's like, all right, now we are going to make 1,000 of these rockets in this design and it's not going to change at all. You still are keeping the flexibility to change things a little bit, torque things. I don't know that you'd go through and make a wildly different tank right now. Maybe at some point you scale it up, right? But without those huge, massive machines, you sort of maintain that flexibility while you're still dialing things in. Is that the right way to say it?
Yeah, I think that's right. And I would also propose that I'm not sure on this, but I would venture a guess that there's been no rocket in history that's been made 1,000 times. And if you think about that, I think the the Falcon second stage is probably going to be the first thing that gets there. But if you think about that from a production standpoint, that's one of the big things that makes rocketry so expensive is, we don't make these things a lot. Even a super high rate production for rockets is incredibly low rate production for just about anything else, right? And so if you put millions of dollars into fixed tooling in order to build this thing, maybe you're going to make 100 or 200 or 300 of these, and it's just not a lot of units, right?
Especially if you're not throwing them away every time. If you are
That's
reusing
right.
them rapidly or not, you have your fleet and you're operating more like the airline where nobody throws the 737 into the ocean every time you use it once, right?
Yeah.
So you have to make less of them. You don't even need to make as many as you would have if everyone was once and done, right?
Right.
Good deal. Let's see here. We talked about the materials a little bit. We didn't talk too much about should I say payload fairing? Is it a cargo bay or is it a payload fairing? What do y'all call it on a reusable second stage?
Well, that's a great point. We call it a payload fairing, but maybe we should pivot.
Because normally we joked a little bit about it, but rockets, in order to operate more efficiently, sometimes shed pieces. They throw things away.
Mm-hmm.
They don't keep carrying it, and SRBs come off because they're empty of fuel, and the payload fairing comes off because the atmosphere is thin enough that you don't have to protect the payload anymore. Rockets are constantly just throwing things off the side in a very controlled manner. For you, if you want to rapidly reuse this, you have to keep the vehicle sort of intact. And instead of a payload fairing that would deploy and tumble away, and we're like, you can see the fairings, they're falling away. They stay closed until you get to space, and then they open up and let a cargo out. Is that a huge design challenge? It's certainly not things that rockets normally do.
Yeah, I would say it's definitely a design challenge. Shuttle did the same thing with its bay doors, right?
Yeah.
It's definitely a design challenge. There's no question. I think there's different types of missions that can be performed, and you can have these reusable fairings. You may choose to have deployable fairings also in certain cases. But one of the unique things that kind of falls out from using these reusable upper stages is that there's now you're performing 3 modalities in every single flight. You're flying to space, and you have to do some amount of maneuvering in order to align with your landing site. So there's some movement in space that happens, and then there's the return aspect. And it turns out that those other 2 modalities, the through space and from space modalities, are valuable to certain people, right? For manufacturing in space, for various government partners and other things like that. And so there's a compelling case to be made where you may want to acquire something in space and bring it back down. You may want to just bring a hosted payload, have it perform a function, close the doors and bring that back down. There's a whole new set of missions, this whole new class of missions that are unlocked because you already do that on every flight, right?
Right.
And so, like I was saying, there may be cases where you want to use deployable fairings, but there may be cases where you don't, and you want to, have those closed up and bring something back and keep them protected.
I have to ask, just waggle your eyebrows. I assume you've done the math, but can the upper stage re-enter and land with or without the payload fairing on the top? Like if you had a deployable one where you did not bring it back down, is the vehicle still aerodynamically stable when it's coming down if it doesn't have the taper on the back of it?
From an aerodynamics perspective, it actually prefers that because when it's coming back down, you want it's all about center of pressure versus center of gravity. So you want center of gravity as far forward as possible, and you want center of pressure as far back as possible. With no fairings, you get rid of mass at a very high position in the vehicle stack. And you create all this drag in the back because it's this blunt, afterward facing step kind of on the back. And so it helps both of those things. So aerodynamically actually prefers no fairing up there.
Okay. So it could theoretically come down either way. I wonder how different the flight dynamics are. Like the software has to operate in this mode or that mode. Probably going to get there at some point, huh?
Well, I would say that's heavily analyzed on our end, at least.
Gotcha. Heavily analyzed on our end. Nice. All right. And the other thing you said there was, you can go into space and retrieve something. We talk about space debris a lot of the times. Is it economically viable to retrieve space debris? Is it not? Well, if you have something that can go up there and grab a hold of something and then enclose it and bring it back, maybe it doesn't need to be enclosed, maybe it does, right? I don't know that we're there yet, but maybe one day we will need to bring some things back. Maybe more immediate is the ability to study things that have been operating in space for a long time. We don't have a lot of capacity to do that for discrete satellites and stuff. We have the ISS. The shuttle came back, right? But being able to go up there and retrieve a satellite that's been up there for X amount of time, is that something that you're looking at, like as a service?
Yeah. If it makes sense, if there are customers who want some. But I would say also, there's other, logical use cases. One of them is manufacturing in space, right? Anytime you manufacture something, you need a constant supply of raw materials to that manufacturing center, and you need a shipment of finished goods, right? And so you can imagine a scenario where you're on the way up delivering raw materials and on the way down bringing finished goods and byproducts, trash, whatever that may be. So that's one example. Another example would be space stations. One of the things that I'm super excited about Starship being successful is I think we finally will have viable commercial space stations. That's awesome. I would imagine that everybody listening wants that to happen. But once that very large infrastructure is put in place, you probably don't, as much as we all love astronaut ice stream and the novelty of it, probably don't want to be eating stuff like that every day. And so what you want is a constant shipment of food, or fresh food, produce, whatever that may be, supplies, etc. And then you need a return mission of trash. And so you imagine these different type of use cases or verticals, and there's a constant supply of goods to and from that location, and those are very easy to kind of comprehend. There's something else I was going to say, but I'm forgetting it.
Let's see. We're talking about going to and from space. That's something that we would, I think, all love to see. Rocket fans who like to see rocket launches and rocket landings. If there was more reason to be going to and from space, not just deploying satellites or just taking things up to the 1 or 2 or 3, the small number of space stations that we have, right? Imagine one day if there are 10 space stations or 20 space stations or orbital factories, like you said. You don't even maybe need people up there all the time, and you're just delivering raw materials and then picking up goods and bringing them back down and then landing them softly, not trying to splash them into the ocean and some of the things that we do. I, for one, hope we see that soon.
That's what this is all about. That's the future that we all want, right? And and you got to figure out how to do that in a way that's both scalable and sustainable. So this was the other thing that I was going to mention was, the other thing that Starship does is puts millions of pounds into orbit, right? That's great. But then what happens to it? And I think that's a highly unknown question, right? You have millions of pounds of heavy metals or rare metals coming back, and if the way that we bring those things back is to burn them up in the atmosphere, at some point that's going to have an effect, right? And I think that's only just beginning to be studied now. But is it viable? Is that the right way? Just burn stuff up in the atmosphere and let it crash? I guess my hunch is probably not. I don't know, right? That's got to be studied, but I don't know.
Yeah.
And I think we'll probably want to collect things and bring it back. You asked the question, is there economic reason for us to collect trash and bring it down? And today, unequivocally, the answer is no. Who's paying for that? Nobody's paying for that. But at some point, I think there is regulation where you can't do what you want to do in space unless you clear your trash. And then it gets built into the cost structure of the economics of space activity. And then there is a paying customer, and then you have to do it. Right?
Yep. I mean, it really is the way that that space operates right now. We have things, they go into operational orbits, and then they either are done and they come back down and burn up, or they get graveyarded out, and it's basically just a junkyard, like a designated parking space for junk that we're done with. And we just leave it there. And we shouldn't probably operate that way forever. But there's no incentive otherwise. Like right now, there's nothing that says that a company needs to, you have to move your satellite to the trash orbit, to the graveyard orbit,
Yeah.
right?
Well, the closest thing we have to it is you have to have a deorbit. From the time your satellite dies, it has to be out of orbit. And that just got switched from, I think it was 20 years to now 5 years. There's not
Like
really
a
a great
plan
way
to
to
do
police it, though. Yeah, you have to have a plan. That's part of your FCC license.
Yep.
There's not a great way to police it, though, other than refusing future licenses, which, may or may not happen.
Hasn't happened yet. There's been like the shot across the bow
Right.
that happened a little while, like months ago,
Yeah.
but there hasn't been a thing where that's really built in. So I don't want to overdo it too much, but it almost is. There's no incentive to do it. There's no, besides you have to do it.
Today,
Or we
there's
might
no
not.
incentive. That's all I'm trying to say. Today, there's no incentive to
That's
do
right.
it. And I think in the long term there will be, but it's going to take some time. It takes more study to understand, what are the actual impacts, and it's literal acts of Congress that we're asking for here, or we're talking about at least.
Well, it's almost like safety training, right? Like there are regulations that say you need to be able to train the folks you work with to work safely, and so there's safety trainings. And then an entire industry has come up around training employees safely, and you can go hire a company that handles that for you, right? And we don't have that with orbital trash cleanup yet, but one day there might be a thing where that is a service that a satellite operator might go and buy from somebody. And so having the vehicle that can go to and from space and bring things back down and sort of operate in all those different modes makes it sort of the orbital tug and tow truck. I don't want to like demean what a vehicle that is fully reusable could do, but it could do things like that, right?
Yeah, I think here's at the end of the day, what you want, what we all want, what customers want. You want a couple things out of space mobility. The first thing is you want it to be low cost. The second thing is you want it to be much more on demand than what we have today, right? I mean, if you want to buy a standalone Falcon 9, it's like a 2-year lead time, which is great, right? There's lots of demand, but it's a long lead time. And if you think about if you're a startup and you're trying to figure out how you're going to get to space, like, do you want to use your very early seed dollars to reserve a spot in line for launch? No, you want to use it to prove your technology. So there's a balance there. But so you want low cost, you want on demand, and you want high reliability. And I think actually the beauty of full rapid reuse is it attacks all three of those three things in at the fundamental level. So you get into this kind of virtuous cycle. The lower cost you have, the more demand you have, the more frequently you're flying. The more frequently you're flying, the better your reliability and the better your availability. And it just feeds on itself. And that's beautiful. That's what you want, right? We're starting to see that is what Falcon has started to show us as an industry. But it is, I would comment that it is still like very, very much day one in our industry. And what rapid full reusability is a whole nother order of magnitude in cost. And the same is true for availability, and then reliability follows as well.
Makes sense. There's a question that I've seen float through chat in a couple different formats here. But you mentioned the cadence, right? Like the more payloads you have to send, the higher your cadence is, the more experience you get, the better you get, because you have an excuse to be flying. And it's great if those are paid for, right? You don't just fly to fly. If you have a paying customer or a service that you're providing by flying these payloads, it's good for you because you get the experience. And we see that with SpaceX and Starlink. There are so many launches that happened, and we're over here broadcasting launches, and we're like, oh, it's another Starlink at 3 a.m. Great. But because of that product that SpaceX has made, they've sort of created their own demand to launch their vehicles, and then they improve their vehicles, they improve their cadence, they get the experience. That is a brilliant way to do it, right? How is Stoke sort of approaching that? Do you have anything in the plans where we're going to launch this many vehicles this many times to help us get this experience? Like, you need payloads, you need excuses and funding to launch vehicles.
I think that the right way to answer that, I think, is it also feeds into the size of the vehicle. You want to have customers. You want to have enough customers who want to go to the same place at the same time always. And if you build the vehicle that's too big, then you can't fill the metaphorical seats of the vehicle, right? So if you think about, a great analogy is the airline industry, right? You have everything from Cessnas to A380s. And in the middle, there's a sweet spot where there's enough people to fill the seats who want to go to the same place at the same time, all the time. And those things are flying all the time. Those are the 737s and the A320s, right? A380 is already out of production because it's so big. It's the cost
big.
structure it's too expensive, and they can't fill the seats, so you can't fly enough,
Yep.
right? And
And
so I
we
guess
also
that's
have. Go ahead.
I was going to say that's what led us to this medium class of rocket, where I think there's enough other commercial customers who are going to want to. We'll be able to fill our seats on every flight, and really, we're actually the limiter, not the demand side. We'll fly as frequently as we possibly can, and there will always be demand, right? That's what you want. You want to be always pushing yourself to fly more frequently.
Gotcha. Because we're almost, I don't know, chicken, egg, cart, horse, demand before the supply, right? We're not in a situation right now where we have 15 commercial space stations and 20 orbital factories that are making crystals that are better to make in microgravity or low gravity, whatever you want to call it, right? We don't have that yet. And
no, but we are.
What do you do
we do have. We do have probably 100 different satellite companies building small and medium sized satellites, and they're all trying to get to orbit. And I think what a lot of those companies are finding are that their rideshare missions with Falcon 9 are great for proof of concept demo missions. But once you have to actually deploy a constellation where satellites need to be phased out in a way that works for you, those rideshare missions are no longer ideal, right? So now what do? You're not going to buy a whole Falcon 9 for these small things. You need something else, right?
Let's make sure everybody understands that real quick, because I think a lot of people miss this. It's like, oh, I'm going to space, and I'm in space, I'm good, right? Well, you don't just want to get into space. That's like saying, I want to go to the US, I want to go to Germany, right? Okay, well, you're in Germany. Did you get to the right city where the tourist attraction you want to see is? No, you need to go to a specific place in Germany. You need to go to a specific place in the city. And so the rideshare is the plane that gets you to the proper country, right? But there's a lot of other places that you need to go. If you have something and you stack a bunch of stuff into a ride share and you launch a bunch of them into the one orbit that you sort of end up in and get dropped off at, then the satellites have to make their way to their own orbits, right? And so then your satellite has to have more capability. You just use the term phasing. They have to be able to move into the useful spot that you need them. And the useful spot isn't always the spot that the rideshare drops them off, right?
Yeah, that's right.
Yeah. So when you have a smaller launcher, a medium launcher, then you can get put to the right building in the city, right? You get the exact destination that you're trying to go to, as opposed to, well, I got on the train and I ended up downtown and now I have to make my way to wherever it is that I'm going. That's where you get into the more specific orbit, not just ride along with everybody else.
Everybody would rather fly direct than have layovers. And there's a very real time value of money associated with this. If a lot of these orbit phasings take 6 months, 9 months to get from drop off location to final location. You even see that in Starlinks, right? And for a company, if you look at it on economic terms, for a company, that's time. It's like dead inventory, right? Where you are not in manufacturing and you are not making revenue, right? So there's a time value of money associated with that. When you'd rather do what satellite companies want, and what our goal is to minimize that time from the time the satellite leaves the factory, the time that they're making revenue. And that's where more frequent direct missions closer to the final orbit come in. And I think that's the role of medium class rocket, provided that it can operate quickly, right?
Gotcha. And especially if it's a new type of medium class rocket, or second stage, I guess you could say, where the second stage is actually reusable. You're not making a boutique bespoke stage for everything and then you're done with it, you use it once. That changes the game, because you can bring that back down, use it again.
That is, by the way, I think, as I understand it, that is the flight rate limiter for Falcon 9 is second stage production. And it's kind of incredible. They're making 100 of them a year. That's kind of incredible. But how do you scale from there? You scale by scaling your factory, which is very expensive, et cetera, et cetera.
Yep. And all the other processes that go into it, because they're testing them, right? SpaceX tests those second stage out of McGregor, and you're putting them through the entire workflow, not just putting welds on metal, right? But everything else that has to happen before that thing goes on top of a rocket and ships a payload. And that's something,
engines, avionics, fluid systems, everything. It's all got to be certified, right?
Everything. And you had mentioned you don't start with a second stage and, let's shoehorn this into full reusability. That's something we've heard of before. Maybe we'll make the second stage on the Falcon 9s reusable. And that's sort of, I haven't heard much about that recently, because that would be shoehorning this extra functionality into something that wasn't designed from the ground up to do that. And you're not doing that, right?
Well, my understanding is the result of that work was to go build Starship.
Was the Go Bell Starship. There you go.
Yeah.
So let's see here. I'm going through chat questions here, y'all. We're sort of jumping around to all sorts of different things, but let me see if I can't grab some other questions here. Did y'all intend to use the Aerospike? That's different. The Aerospike effect, or was that just like we solved all these other problems and it's a bonus of the resulting solution there?
Yeah, I think it's that latter part, right? We kind of backed our way into it. First, we started to think about, how do we make short, squat nozzles that are robust to the aerodynamics, and eventually it led to this configuration where the thrusters are all on the outboard side, and then you're always trying to improve efficiency as much as possible, and once you're there, it's kind of silly to not use it.
Yep, makes sense.
But there's a lot of other factors, right? Reentry aerodynamics have as much a say in that base geometry than engine performance.
Gotcha.
And that's why it doesn't look like a traditional Aerospike.
Doesn't look like a traditional Aerospike with the actual spike at the bottom, because that's not intended to also work as a heat shield, I guess, right? Regardless of, I played a lot of Kerbal, so every time I think of something, I'm like, oh yeah, like in Kerbal. So if I'm saying Kerbal too much, I apologize. Just, sort of where I came from. Let's see here. Mission duration. We're talking about a second stage that can be reusable, because there's going to be questions about the booster coming up here as well. But mission duration for the second stage, there's complexities with lifetime in space. How long something can stay in orbit and continue operating. In the renders and stuff like that, have I seen things like solar panels? Or what have you done? Like, what are you shooting for, I guess, is a good way to come about that in terms of the mission duration for the second stage?
I think the timeline is also appropriate there. It depends on when we're looking and what the missions are. But out of the gate, we're looking to get up and come down within a couple days in order to rephase with the landing location that we care about. So I would answer it this way. We'll start out with relatively short missions and look for ways to elongate or lengthen the missions over time for certain use cases.
Makes sense. So it starts with sort of the delivery mechanism where you're going up, you're done with it, you're coming back down. You're not living in space. It's not an orbital factory that you've installed because the second stage lives there. It may deploy something, or it may visit somewhere and drop something off, pick something up, but it doesn't stay in space for a long time. But then you go towards that.
Yeah, I imagine the motivation there was, thinking about cryofluid management and power systems and all those things. And it's something that certainly we think about all the time.
Yep, makes sense. Let's see here. A lot of different questions. Some of the questions, folks, I am rolling together. Yes, this is a very cool discussion. We're glad you like it. Just like saying some things that people are saying. Different orbits. Are you looking to serve any sort of specific orbits? Are you polar orbits? What are you sort of
we want to be able
to
go we want to be able to go to any orbit and at any time. That's the way we think about it, and it's one of another great byproduct of hydrogen. It is a very high performing fuel, and it allows us to do some of the higher energy orbits that would otherwise not be accessible by a smaller medium class rocket. And so we do have very meaningful capability to higher energy orbits.
Gotcha. I'm speed running a couple different questions here to get some of these chat questions in. So y'all keep tagging us at NASASpaceFlight. If I can ask, just give me the knowing eyebrow waggle, but there's a lot of people asking about crew ratings on anything that Stoke has looked at. Something you've looked at, not your first thing, eyebrow waggle.
It's definitely not the first thing. I think the way we've sized the rocket and what we're looking for is to respond to a known commercial demand, and I think that is right now focused on satellites and not humans. I think in time I would love to do that, but it's definitely not what you want to do for your first rocket as a startup. So yeah, that's where I stand on that.
Makes sense. I mean,
by the way, we talk about supply and demand and size of the vehicle. I actually expect that we'll see a kind of a bimodal distribution in those optimal size of the vehicles. One of them is designed for satellites, and one of them is probably bigger, designed for humans with life systems.
Is it that technology has gotten us to the space where satellites don't have to be as massive as maybe they used to be? So satellites that don't need life support systems and stuff can be smaller, but once you put a meat bag in it, you're sort of like constrained to the size of a human being, so you have to
You got to
serve the size
control
of the
temperature. You got to give that thing oxygen. You got to give,
Yep.
all kinds of stuff, right?
comfy seats, like the whole thing.
Yeah.
Cool screens
Yeah.
to watch TV on or whatever, to watch movies on.
Right. That's right.
I joke, but it makes sense. Like, we're not really making humans any smaller, but other technologies, like you could put in a satellite, have
Yeah.
gotten smaller. Or you can put more
Yeah.
functionality in a satellite.
Well, that's a huge part of it.
So-
And that, when we talked
Yep.
about the main ingredients coming together to have what we need to create a vibrant economy in space, that is one of them, right? You can do very powerful satellite systems today that, in pretty small form factors that, in the 90s, when this was that was like the last wave when we tried this commercial space thing, it kind of petered out. And that was one of the big reasons, right? Yeah.
Yep. Just the state of technology, and it comes down to mass. Like, when technology is bigger and heavy, that's more mass you have to put in. I don't know that, obviously we're probably more mass constrained than volume constrained usually for things like that. I don't know if that's true or not. That's what I think, right? If I had to make it up. But as technology has improved and battery storage technology has come down and electronics have gotten smaller and lighter weight, you can pack more function. Hold up my cell phone, right? Like, look at my cell phone. What a wonder of technology. So, let's see here. I've asked those. I'm going to keep you up. Yes. There's like 50 questions on the crew vehicle, so I had to ask. No, it's not going to land with the helicopter blade. It's passive or that's a Roton different thing.
Yep.
I saw on the website the mention of passive systems, right? So when we come down and we're landing a payload, we have different ways to get rid of that energy and come to a stop on the surface of the Earth, right? And we have the heat shield that helps us slow down by slamming through the atmosphere. We have wings that help us glide and bleed off energy. We have parachutes like we see on crew capsules. Shuttle had wings. Crew capsules have parachutes. You have rocket engines. We see Falcon 9. Rocket engines is another way that you can land.
Yeah.
Do you have or plan any backup systems for your landings? Like, everybody's seen the little plane that also has the parachute in case the engine fails and it can't glide or whatever. Do you have any designs for backup systems like parachutes?
I would say no. And that's another reason to not address the human flight kind of paradigm today, is because we want to demonstrate and prove the technology, and we don't necessarily need triplex redundancy. With that being said, we've got a whole ton of thrusters, and so we do have the ability to, if one of those malfunctions, we do have the ability to kind of accommodate that failure.
Gotcha.
But we do only have a common set of pumps, right? So largely
it's a
single
trade-off.
string.
It's a balance.
Yeah, exactly. Right now we're focused on proving the function, delivering satellites to orbit, and I think that's the right place to focus today.
Gotcha. So you said triplex redundancy. What's the duplex redundancy now? Is that just in the number of combustion chambers, or what is?
Well, typically for human-rated systems, you want your critical systems to be something like triplex. Obviously, with engines, that's never the case. But then you say, all right, if an engine failures, then you're going to save the human some other way. You're going to separate. You're going to have an escape pod. You're going to whatever it is.
Gotcha.
Yeah. Right. So that was that reference. Duplex redundancy would be, engine out scenarios, things like that.
Gotcha. So that's more of there are 3 main parachutes and we can still gently land on 2, versus we have parachutes and we have thrusters and we have wings and like that sort of thing.
Yeah,
more of the same thing, which you have in engines, 30 combustion chambers, I guess, nozzles around the outside. And if one's having an issue, you can shut down its partner on the opposite side, and then you still have balanced thrust, et cetera, et cetera.
Right.
All right. So this is a technical question from me. When you are changing the thrust of the ring of, I keep wanting to say engines, but the ring of engines, the ring of nozzles on the bottom, so that you can do the translation like we saw in the hop, right? Is that just you reduce the thrust in a couple engines on one side and everything else keeps going? Or is there like a gradient of thrust reduction across you were to slice it? How do you do that? Is that a thing?
Well, that's it's how you design your GNC algorithm. GNC being guidance, navigation, control, right? And keep in mind also, you'll see that in the hop video, the thing has a slow roll, right? And so what you want to prove is that you're insensitive to that roll also. Okay. So, yeah. So I think, you can, there's a number of different ways you can slice that pie, and, we do it our way, and it seems to have worked.
Do it your way. Gotcha. So can I ask this? If there is a little bit of a roll, like look at the legs there and look at the vehicle rotating on its long axis. When you don't have, like when you have the differential thrust the way that you have it, how do you deal with roll?
With software.
Very
right? So that's
with software.
Yeah, very, very carefully, right? And that's the point of the comment is that, it depends on how you design your GNC code. And yeah, you have to think about that roll is obviously affecting your differential throttle scheme, right? Yep. So you still have to have that TVC control while the vehicle is rolling. And yeah.
So as the vehicle's rolling, the thruster that is like the direction it's moving is going to change. And so you can't just, turn that thruster down a little bit and let it start to go. Yeah. If the vehicle is moving, the thruster that is, I guess, in the direction of movement changes as the vehicle rotates. And the software has to know that and think about that, right?
If you go through, I don't know what social media was, but I'm pretty sure we put it on X and maybe YouTube or something. Sure. But we did these tests called we called them the hula hoop tests, where we'd basically, if you imagine the thrust magnitude, it's higher on one side and lower on the other, and then we kind of like rotate that around in a circle. So we did that partially to test the effect that I just discussed, but also to try to incite different feed modes in the feed manifolds and prove that we were robust to anything that we could set up there. But yeah, so that kind of touches on it right there. You can imagine the hula hoop test, the kind of like distribution of thrust all around the perimeter rotating around. If you change reference frames and the vehicle is actually rotating, then that kind of thrust plane is static in the ground frame of reference, right?
Gotcha.
So you kind of have
Makes
the same
sense.
thing.
I want to keep asking all these questions about exactly how you control it when you're not allowed to move your engines, because it really is. It's not the way that it normally works. And you have auxiliary systems, you have these other thrusters at the top, and these sorts of other ways you can solve it, right? But let's talk about a couple other things. There's a question here about, isn't it more complicated? Are we looking at the hula hoop test there?
I don't think this is it. Maybe.
So. It's just an engine test. We're good. It's fine.
No, this is definitely not there. This is on the hopper static fire stand. This, not the test stand.
It looks like it's competing for the most metal of rockets with the flames coming out the top there.
This is a proof of concept thing, right? So we hack. The thing at the top is actually the flare. We flew the flare stack, which you wouldn't do on an orbital vehicle, right? But it was the easiest way for. Right. It was the easiest way for us to handle that for this, right? All these things need their own ground systems and whatnot. And, we want to prove the technology with this thing, not do more. Yeah.
Gotcha. So the other question here, normally you have a rocket engine, there's however many in the middle. It's so simple. There's just one place for the engine to push on the rocket, right? But it's a little bit more complicated than that, because the rocket body doesn't have like an internal girder in the middle of it that translates the force through the rest of the vehicle. In most rockets, the skin of the rocket is what carries the rest of the rocket up. On the booster, carries the second stage carries the payload. I would imagine that you get some efficiencies from applying the force. Let's say apply directly to forehead, but it's not that. It's to the edge of the ring, right? Yeah. And when your engines are pushing on the bottom of the main body of the rocket, that seems like it would be better.
Well, no matter where you generate the thrust all has to eventually move up the skin, the outer diameter of the vehicle, because that's the only place there is structure through the entire vehicle. So whether you have, how many does Starship have now? 30 on the stage one, 30 engines, 30 Raptors. whatever it is.
33,
It's
37,
basically
9.
whatever it is, basically a gazillion engines all along this like flat platform, let's say. You still have to get that thrust out to the outer skin of the vehicle, and their thrust structure is what does that. However, you can now they need to do that because you need absolutely massive thrust. Upper stages have much lower thrust.
So many engines in there.
And yeah, exactly. Upper stages need much lower thrust for a given performance. And so what we do is we create all the thrust along the outer skin of the vehicle and keep it there. Now, if we were let's say we wanted to gimbal the whole base of the vehicle, which we did think about at one point. If you wanted to gimbal that whole heat shield structure, you'd have to take all that thrust, all that basically force, and bring it into a single gimbal point in order to be able to swing it around, and then distribute that load all the way back out to the skin, which structurally is extremely inefficient. So that also points to the quality, the differential throttle ability helps you there as well.
Makes sense. I think about that. If you have the bottom of the rocket stuffed with engines or whatever, you have to have a beefy structure down there that the engines are attached to, that then takes that force and translates it to the body of the rocket, which is literally just the tank going up the side. Right?
Oh, there you go. You found there's the hula hoop test.
There's the hula hoop versus the traditional thrust vector control. Nice. But here, is it just sort of the heat shield in the bottom of the tank, but it can be lighter because you're not transmitting the same load through that? Is that a true statement, or am I going a little bit too far there?
Yeah, that's right. The tank doesn't have to take a punch load in the center of it. The load is always go up through the skin of the vehicle. Yep.
Gotcha. So you've removed some mass that is not fuel or payload from the structure of the rocket, so the rocket gets to be a little bit more efficient because you've put engines all around the outside, like we see here in the animation.
Yeah. Yep, exactly.
I want to fly that. I want to go and build that and see how that flies, like how you actually change the thrust on so many different engines at once. Let's see here. We've barely talked about the booster. The upper stage is so different than what we've seen. I wanted to talk a lot about how that works. Tell us a little bit about the booster that's going to carry this on its way to space, like the first part of the launch.
Yeah. So I would say, again, that there is kind of a playbook for doing this in a reusable way. Ours is methane oxygen. We just see a methane oxygen vehicle hopefully make orbit today. That'll be exciting. But methane oxygen, yeah, it's getting there. Okay, so it's methane oxygen. We have 7 engines on there, building our engines right now. They're full flow stage combustion. I would say, it's kind of cool to be able to say this, but from there, relatively traditional reusable first stage. 5 years ago, you probably couldn't say traditional reusable first stage, but now,
I
think we can.
Nice. I like it. That's a cool thing to be able to say. I can see down at the bottom we've got some landing gear that will deploy in a traditional rocket landing. I guess I don't even know if that's the right way to say it, but doesn't look like they're copied. We get this comment on occasions like, "Oh, those are just like this." And it's like, yeah, but physics and triangles. Like as it turns out, physics likes triangles for things like this. There are only so many different ways you can style up a triangle if you want to efficiently transmit a load, right?
Yep,
so
that's right.
You've flown Hopper. Hopper's gone on its second hop. Where are you at with the fully reusable stage 1?
Well, we just released pictures of our what we call the dev tank. The dev tank was everything. Last year we built. We broke 100 people on January 2nd, so it's still a pretty small team, and that covers all of integration, test facilities, manufacturing, and then all the engineering, and dead weight overhead like myself. But yeah, so there's our dev tank. The way we designed that was to include all of the complexity of the full stage tank, but not have the full length. And the idea there was to prove out the manufacturing processes. We built basically three vehicles last year: Hopper 1, Hopper 2, and this thing. It has a common dome in the middle. It has a downcomer. It has the propellant distribution system. And so we did all that. We shipped it. We did the pressure proof testing on it, and now we brought it back in. We're going to do integrate the rest of the fluid systems management systems in there. We'll do basically, let's call it wet dress rehearsal style activity with that to prove out those systems. And in parallel, be building the next tank, which will be full length. So this has all of the complexity of the real deal. The only thing that it doesn't have is we didn't include all of the barrel length sections. So it's not as long as the full length tank. We just did that to save time, cost, shipping, pain in the ass level, etc. We're going to get all the technical benefits out of this thing while also making it as easy as possible.
Gotcha.
So that's where we're at.
I don't know if this is the right.
Yep.
Yep. I don't know if this is the right way to say it, but it's sort of subscale in one dimension, right? The fiddly bits, the complicated bits are there. The ends of it, the diameter is the same. Like all those complex parts are there, and you just didn't put in extra ring sections, so it's a little bit shorter. Right? Subscale in one dimension, I kind of like, but I don't know if anybody else would say that.
No, you nailed it.
You know
That's
what I mean?
Exactly right. Yep.
Okay, cool.
Yep.
So you've gotten through that. You're going to go through all the processes and procedures and get the experience, put it through the cycles, heat it up, cool it down, pressurize it, let the pressure out, all that sort of stuff to learn how this design and these materials sort of behave the way you've put them together here, right?
That's right. Yep.
Cool. All right. Let's see here. We're coming up on our hour and a half. I don't know if it's felt like an hour and a half to you, but I could sit here and continue chatting about random things about your cool designs and rockets for a while. Is there anything, Andy, that we didn't cover, like that we didn't ask or didn't talk about that you really wanted to hit on here?
Well, I appreciate the time for sure. Like I said, we're a small team. I think we've done a lot in a little time. We've been pretty efficient with the capital that we have raised, and all of that is to say is just a huge testament to the team that we've put together. They're really working hard and kicking butt, and just really impressed by everything that they've been able to do. So it's a huge testament to the team, and we're just excited to keep going as fast as possible and hopefully make this kind of holy grail of rocketry come to life.
Yeah. Absolutely. It really is cool. You go through here and you see all the different people that are working on things and folks just solving things, coming up with ways to do things, trying new things. I think that it's fantastic that y'all are able to try new things in a responsible way. Like the physics backs it up, right? You can throttle the engines like this, and physics says that that should be a thing. Rocket science versus rocket engineering. A lot of times it's hard to make those things happen in the real world, even if the physics and theories and stuff like that work. But y'all have booked a couple of successes so far.
We looked for people who think from first principles, who kind of are sober in that way, but also still free spirited enough to think of new ways to solve problems. And that's what we talked about today. And that's through every system in the vehicle. Yep.
Good deal. Good information. Like physics isn't changing. Maybe our understanding is changing, but trying out new things, especially. It seems like we have lots of ideas and lots of papers from when we first started to go to space, right? Like all these different things that were tried and thought about, but not everything really made it. And now trying, like circling back around with the latest technology we have, the latest things we can simulate, run it through the computer before we have to build it and fly it in real life, but then eventually do get the ground truth, sky truth, space truth, whatever you want to call it.
Well, at the end of the day, we all answer to physics, and we always will, right? So you gotta solve that part of it.
Absolutely. All right. Well, folks, I did get through a good number of the questions there. I'm not able to ever get through all of the questions. I hope some of them I rolled together, and we did jump through some of the things there. It doesn't even feel like an hour and a half. I just love learning more about things like this, especially when it's like, yep, we improved efficiency by just doing the same things better than they were done before. Like y'all have new ideas, you have cool new things, and I can't wait to see what y'all fly next. What should we see? What do you think we're going to see here next? Do you have another hop coming up, or next thing?
Well, the hop is the place that we do the hop is pretty close to an airport, and so that is actually what limited the scope or the altitude of the hop, and it answered all of the technical questions that we had for ourselves on that test program. So we're not going to hop that thing again. We're going to focus on first stage development, first stage engine. Hopefully we'll start to roll out some of those milestones that we're working hard on. First stage tank is coming right along, and so you'll start to see those things. Oh, we'll fire the engine with all 30 thrusters on the second stage engine. So it's a development path, and the next step, in a real sense, is orbit. So trying to knock down all the things we need to do to get from here to there.
All the myriad things that are required to go from cool ideas and rocket science to rocket engineering with things that are actually floating through space. So, Andy,
right.
thank you so much Thank you so much for the time here today. I really do appreciate you taking time out of your Sunday to sit here and just chat with me and let me ask random questions about all the cool stuff that Stoke is working on. Folks, you saw, we put on the screen there, we should put the clickable link in chat as well, that tweet. If you're interested in careers at Stoke, there was a tweet that came out with the new year there about the facility and stuff like that. Head on over, and if it's something that you might want to see if you can be involved with, that was over there as well. Make sure you follow them on social media too, because y'all are releasing some cool things. There's that tweet again. Yeah, there you go. It's at Stoke_space over on the Everything app, stokespace.com/careers. Andy, just thank you so much for spending time here to sit down and talk with me.
This was fun. All right. Thank you so much.
Now, as you can clearly see from that video, Stoke Space is using a very advanced second stage to make it completely reusable. If this works and they get a booster able to lift the thing properly, then it will be better than Neutron, and in many ways better than the SpaceX Falcon 9, which just has a reusable first stage. You see that they're using an actively cooled heat shield, metal heat shield, and they're just pumping a little bit of their cryogenic propellant through it and letting it exhaust out during the re-entry phase, and then they fire up their engines. Now they're using thrust chambers all around this big dome and making a large Aerospike. Now he's talking about doing things no one had ever done or thought of. But if you go back to the Chrysler Serve, this is pretty much the Chrysler Serve design, except for the actively cooled heat shield, which I think is an incredible innovation.